Good morning. Sabah al-khair. Very good morning to everyone in Qatar from the Cyprus Institute Green Room. I hope you can hear what we are saying. Unfortunately, the Cyprus regulations now require us to wear the mask in any space inside or outside where there's more than one person. So do let us know, please, if it is difficult to hear us. I see our project coordinator, Axel Caprolat, agreeing that we are audible. So therefore, I would like to go ahead and give you a very warm welcome indeed on this Tuesday morning to this special edition of the BEATS Beamline for Tomography at SESAME project and the user community building event for Qatar. And we are very, very happy indeed to have you join us this morning. I am Kirsi Lorenz here at the Cyprus Institute Green Room, joined by my colleagues who I will introduce later. But now it is time for the opening address of this event. And before that, I would just like to very briefly introduce Dr. Temadher Al-Madid, who holds an MSc in Modern Applicable Mathematics from Sheffield Hallam University, and she has kindly agreed to give us the opening address today. She holds a PhD in mathematics from University of London on variations of Elgamal-based key agreement protocols. And in 2005, she also earned the PGC in teaching to inspire learning from University of London in 2005. She has over 12 years experience in teaching mathematics to university students as well as researchers. Dr. Al-Madid, we are grateful and that you have been able to join us today and eager to hear your opening address. Please.
Thank you very much for the introduction. There's an echo. Bismillah ar-Rahman ar-Rahim. It's my pleasure to welcome you all to the first specialized workshop to build up the core community of researchers from Qatar as future potential users for the BEATS, the Beamline for Tomography at SESAME. I would like to first thank the Cyprus Institute for organizing and hosting this workshop, mainly Dr. Chris Lawrence, who is behind this event. Many thanks to Dr. Andrea Lausi, the scientific director of SESAME, and also all the key speakers from all over the world presenting this kind of research opportunity for multi-applications and interest to researchers in Qatar. I don't want to forget thanking the local organizing committee here at Qatar University who worked hard to have this event available. Thank you all for attending, and I wish you all the success and useful information from this workshop. And thank you very much.
Thank you very much indeed, Dr. Al-Madid. It's really a great pleasure to hold this event in close collaboration with our Qatari colleagues. And I should specifically mention key people at this point who have made it possible for us to hold this event and to reach out to you to explore together the research opportunities that the BEATS Beamline and the SESAME synchrotron offers. And I would like to extend a very special thanks to Dr. Mohammed Garaibe, who is, of course, a member of the SESAME Scientific Advisory Committee, as well as a researcher and faculty member at the Qatar University. We will be hearing from him later on, as well as, of course, Professor Ilham Al-Qaradawi, and she has been really a key component of also organizing this event. So I would very, very much like to thank you and of course, all your team and our collaborators and co-organizers in Qatar. And we shall be privileged to hear from both of you later on today in the panel discussions, as well as tomorrow. So now, unless someone would like to make further opening remarks, is there anyone who would like to make any further opening remarks at this point? So in that case, we shall go on to the first talk by the project coordinator, BEATS coordinator, Dr. Axel Caprolat. But prior to that, I would just like to go through very briefly some housekeeping matters. So the event is recorded, and I trust this is okay with everyone. It will be made available through the BEATS website for further viewing. Is there anyone who does not agree with this? I take this as agreement. The important thing, if you are needing to pop out for a little bit from the workshop and wish to come back, make sure that your screen name matches your registration. This is for cybersecurity. We have our IT staff here checking that it is the registered participants who enter this webinar space. During your talk and other people's talks, you can of course keep your video on, but unless you are the speaker, kindly keep the microphone muted. This makes a nicer environment for all of us. In order to ask questions, you can write your question in the chat or raise the hand option. You're of course very welcome, if there is a suitable moment, also just voice your question, but to ensure that we notice it, given the number of the participants, it would be very much appreciated if you can use either the chat or raise your hand. And we have members of the team here, Dr. Simona Lemmers and Ms. Sila Kayal, as well as Yuko Miyauchi and Mr. Angelos here at the Cyprus Institute following these questions. If you have technical issues, please send a message by chat to the host here. And later on tomorrow, when we have the breakout rooms, before the breakout session, put the number of the room you would like to join in front of your name on this platform, and we will then allocate you to the specific room. The rooms are in the program. We can have a look at them tomorrow again, prior to the breakout sessions. And if you would like to move to a different room during a breakout session, please send a request by chat to the host. We'll talk about that again tomorrow. And in case you do not select a room during the course of today, tomorrow, you will be moved to a room of the choice of Mr. Angelos here at the Institute. So do select a room. And for the speakers, just to remind you, the talk should be allowing also for questions and some discussion in the end. So please try to retain some time for that. Talks could be 20 to 25 minutes to allow for that. And there will be a notice of 5 minutes, 3 minutes, and 1 minute remaining before the time limit. And Scilla has just demonstrated the note. Can you hear that? Good. Wonderful. So without further ado, we go now to the first speaker, and of course, as is appropriate in such workshops, such events, our first speaker is the man who knows all about the project, Dr. Axel Caprolat, who is the BEATS coordinator. And he is based at the European Synchrotron Radiation Facility in France. And in addition to being the BEATS coordinator, he also leads a number of work packages within the project. So he has very broad shoulders indeed. Work package 1, work package 4, 1 is on management and 4 is relating to the Beamline technical design report and instrumentation procurement. So now we are very privileged to hear from Axel about the recent updates from the BEATS tomography Beamline project. Dr. Caprolat, please.
Thank you very much, Cassie. Let me try to share my screen. And so I hope you can see my first slide.
Yes.
Okay, perfect, wonderful. So thank you very much for this very kind introduction, Kirsi. It is a pleasure to also, like the people who came before me, thank the organizers and everybody who made this event possible. I wish you a good morning from the Région Rhône-Alpes in France, because as you can see, also we are now hit by Corona a little bit more than in summer, and I'm working from home. So in what follows, I will introduce you to the BEATS project proposal and what we have achieved in the past, let's say, 2 years. I want to start with some words on the history. Such a project like ours has a life cycle. It begins with the European Commission or any other funding agency issuing a so-called grant, where they, following their political steering opportunities or wishes, offer a certain activity to be applied for by partners in the field. And this is then followed by these partners getting together and writing a proposal, which is judged most times in competition with other partner corporations. And then one of them or two get this project and have to carry it out and deliver. It was in 2017 when Yes?
Yeah, sorry to interrupt. I'm just wondering if you could put the presentation screen on. Now you're sharing your screen. So if you're able to make it a little bit larger. Yes, that's it. Perfect. Okay. And in the bottom, there is still the screen logo. If you go to the right bottom, and you may be able to make it even a little bit larger. But now it's suitable.
I think I have shared the wrong screen, I'm afraid. Where can I stop share? Stop. I tried again. This should not be. It doesn't allow me to skip my sharing. That's weird.
The stop share is on the top of the screen.
Yeah, I try to click, but nothing happens. Okay, then we do it this way, and you can see
it. We can see it this size. So if it's okay with you, this is.
No, but continue like this. Okay, good. So the mission here of the European Commission was to reinforce the European research infrastructure and its international cooperation. So it is part within the European research institutes and to the outside of Europe. The scope is twofold, what the Commission had in mind. It is to support the development and installation of a dedicated beamline at SESAME. Please note that they just said a dedicated beamline and didn't specify which one. And with the same weight, to strengthen the links between the European network of the analytical facilities that we have with the particular reference to the new synchrotrons currently under development, which means that we have well-established but also recently established synchrotrons, and also the network between them should be enhanced by going out of Europe and building a beamline there. What the heck is this? There's something badly wrong with my computer, I'm afraid. Good. The proposal then, we put together a, let's say, number of partners in crime to apply for this grant, and we established a proposal. The general aim is fourfold. We wanted, of course, to follow the proposal of the European Commission to pave the way for an efficient operation of SESAME. This you do by just enhancing the critical mass of beamlines. But this would not be of any value if we would not in parallel develop and consolidate the science case and to build up a science community. And that is what we are going here today to do. Then during the proposal phase, it was decided that we would procure a beamline for hard X-ray full field tomography. So we decided what kind of beamline it would be for the simple reason that this is a very interesting field, highly demanded, and also a straightforward beamline to build. And this also explains why we chose this acronym for the project, BEATS. It simply means Beamline at SESAME. Voila, Beamline for Tomography at SESAME. And then a very important issue as well is to address the sustainability of operation by preparing medium to long-term funding scenarios. So it makes no sense to build a beamline, which then cannot, let's say, be used until the end of its lifetime of, let's say, 10, 15, perhaps 20 years because of the lack of funding. So we will look into this as well. So the general spirit of the project is then twofold. As I said, we build a competitive tomography beamline, but we also foster the mutual exchange of knowledge between all the partners within BEATS. That is, how to design, how to procure, how to construct, and how to commission such a beamline. It is very important to understand that this beamline is not just another ESRF beamline or a copy of it, and that BEATS, the whole project, is not just the construction of a beamline. Our aim is indeed to foster, as I said, the interaction between all the partners and to build and include communities, the reason why we are here today. So these two things are part of BEATS. The structure of the proposal is best explained when you have a look at what this beamline is in the first place. So you have a synchrotron or a storage ring in which through a vacuum tube, a long vacuum tube of polygonal character, you have electrons traveling at the speed of light, kept on a trajectory by magnetic structures. These electrons, because they are traveling at the speed of light, when directed in another direction, are accelerated and emit electromagnetic radiation. This ranges from the infrared until the hard X-ray regime, depending on the parameters of the source. This beam, this photon beam, is highly collimated and of a high brilliance due to the fact that these electrons fly at the speed of light. This beam needs to be shaped by elements which we call the front end, then needs to be, let's say, manipulated in its spectrum to be of the right use for the experiment. Here you have a hutch in which you have the sample and the detectors who look at what happens with this radiation when it passes through the sample. This is the way how the sample leaves its traces and information on itself in this outgoing radiation. Of course, you have as well people who control the whole exercise and also do the analysis of the data online if possible. So it makes very much sense to divide the proposal into work packages which deal with these issues on their own. We have a work package which worked on the decision on which source we're going to install and the components of the front end. So these people did the design of the front end components. We have a work package which deals with the technical design of the optics and the experimental hutch, what is installed in there, which means the monochromator and the sample and the detector station. We have a work package which looks after the data acquisition, all the computing that is needed to do this in a most efficient way. Of course, you have then to provide the infrastructure, means the radiation safety hutches, all the facilities, and then later on the assembly and commissioning. These are these two work packages. Then the non-sexy stuff, which is the management and the procurement, but nevertheless important. And again, a very important one, which concerns the sustainability, i.e. stewardship models, funding, science case, things like this. So we brought together 9 partners from Northern Europe over Central Europe to the Mediterranean and the Middle East. And these are let's go from north to southeast. It's DESI from Hamburg. It's the PSI in Switzerland. It is Solaris in Poland. It's from Italy, Elettra and INFN. It is the Barcelona synchrotron cells. It is, of course, the Cyprus Institute, and then goes without saying, SESAME, all coordinated by a big honor for us, the ESRF. We shared a little bit the responsibilities between the partners according to the experience and the competences that were already there. So the X-ray source was looked at by ALBA and by INFN. The technical design of the beamline itself is mostly Elettra, the ESRF, and INFN as well. PSI is looking after the training activities for the staff of all the partners. Sustainability is Cyprus and DESI, and what we call them the recently founded synchrotron radiations. SESAME and Solaris are invited and do so to participate in all these activities, either actively or just by looking over our shoulders. So we have a blend of leading facilities from Europe and the Middle East, and we have well-established ones as well as recently founded synchrotrons together to work on this nice venture. That is the moment when we can say, aha, it is no longer called proposal, it is now called project, because indeed in summer 2018 we won the grant, and we were awarded the sum of 6 million euros for a 4-year project, which started on the 1st of January 2019 and is now to be ended at the end of 2022. This seems to be a lot of money for a single beamline, but before we get dollar signs in the eyes, this is not all for the beamline. As I said, we have another big task in BEADS, that is user community building, the science case building, the sustainability and things like this. So a lot of money goes in that. So in the end, we can say the budget is still, as always in such cases, limited. Where do we stand? As you can see from these dates, we are close to the end of the 2nd year. We foresaw in the first 2 years the design, the technical design of the beamline and the final design phase of all the experimental stuff. This is terminated. We start the procurement of what we have designed, and we expect this to take over the next year. This, of course, all Corona depending. And then we will start as things come in to work on the infrastructure and install. We foresee the radiation test, which means that the hutches are erected, that there is the front end and the source functioning either end of year 3, 21, or in the early months of year 422. In parallel of all these activities, wherever possible, we install the instrumentation that comes in. We do commissioning over the year 4, and we expect, or we hope very much, to have our first what we call friendly users before the end of the project, let's say in autumn 2022. Friendly users are those who accept that the beamline is not ready yet, and there may be hiccups, and they help us with the commissioning itself. What did we achieve so far? As I said, we are halfway through, so you can expect that something is all ready to be shown, and there is indeed quite some effort which has been successfully brought behind us. Nowadays, more than ever, communication is a very important thing, and that is the only interesting thing from the Work Package 1 management that you can report on such occasions. We have, of course, everybody has it, we as well, a website. Here you find, let's say on a monthly frequency, the news on the project and developments. And you find all relevant documents that we can publish. So please note this down and pay us a visit from time to time. It may be interesting. Being modern people that we are of course also on social media, the so-called social media. So believe it or not, we have a Twitter account. This is fed with, let's say, a little higher frequency of once a week or twice a week, and includes as well news. For instance, today's event is of course tweeted, but also gossip. So it is a good idea to subscribe to this one. And if you would be so kind, from time to time, if you really like it, like us or forward us, retweet us, it would help to make beats even wider known. I'll come to some hardcore developments or the deliverables. The first thing, of course, that you look at is the engine of the beamline. And this is a synchrotron. SESAME is a synchrotron with a rather low electron energy compared to the big brothers in Europe. And to use the radiation that is coming from a normal bending magnet would not be suitable for an X-ray tomography beamline, where you need hard X-rays and high flux. So it was decided to go for a device, what we call an insertion device. A very simple one is a wavelength shifter. The electrons flying through a straight section on a straight trajectory are suddenly confronted with a magnetic field perpendicular to their path, which makes them turn, let's say, to the right. So they are a bit out of the trajectory. This is then followed by a very strong magnet, which bends the electron trajectory back to more than the original one. And then you find another magnet which brings them back to the original trajectory, and they leave straight as they came in out of this magnetic structure. So what they do, they wiggle here a little bit. And each time an electron makes a sharp bend, you get electromagnetic radiation. And we managed to arrive at a maximum field of 3 Tesla here, which leads to quite a satisfying spectrum. If you're not too greedy, you can go up to, let's say, 40 or even 50 kilo electron volt. This has been designed by our colleagues from ALBA in collaboration with INF. That is one thing. We know what the source will be. This then, of course, helps a lot in laying out the beamline. This is something that will be presented in detail by my colleague Gianluca Iori, the beamline responsible. It's just to show you that this beamline will be quite an ordinary beamline. Here we have the source. This is within the accelerator or the storage ring. Here we have the source. Here is what we call the components of the front end. The beam exits in this direction and is shaped and manipulated by these components. We have optical hutch where we put the monochromator, and we have a large experimental hutch in which we put a sample stage and detector stage to carry out the experiments. The control hutches are adjacent to this setup. As I said, the details and what is all in there will be communicated by Gianluca. All the details of this technical design were written up in what we call the technical design report. That is an 80-page document, which I put on one page here just to prove that it exists. It has been submitted early September and is approved now by the European Commission. The SESAME Scientific Advisory Committee will have a look at it as well. Initial feedback is that they like it as well. So this is available for those who are interested and proves that the technical design of what we put in the Beamline is decided and constructed. Another big issue is, of course, for tomography Beamline, the data evaluation and analysis. Why? Tomography Beamline might be straightforward to construct, but not always to operate, because due to the high frame rate of the cameras which are used to do tomography in synchrotron radiations, you have to cope with a huge amount of data. Such a Beamline can create easily terabytes per day. And it is not necessarily foreseen within the computer infrastructure that you find even at the longer established synchrotrons to deal with such an amount of data. It is not that you just have to collect the data and then with all leisure do analyze them at home. You need to do an online data analysis and storage to be able to judge the quality of your measurements. So there is a lot of infrastructure that has to be put in, which is not available at SESAME, naturally not available at SESAME, I should say. And this goes to really impressive network connections and servers and things like this. All this, we have the specifications nearly ready, and we can go to call for tender in the very near future. And another big, although soft deliverable is what we call the science case. This is the result of a thorough reflection on what might the potential users be for such a Beamline. How can we address them? What can we offer them? And what would they request us to have installed on the Beamline? Also, this resulted in a somehow 50-60 pages document, which was submitted and is available. But contrary to the technical design of the Beamline, this will continue to evolve until the end of the project itself. Because of course, with happenings like today, we will continue to gather feedback and to put it in wherever we see that it is not yet covered by our document. And then the last slide on what we achieved is not so sexy, but nevertheless has to be, let's say, addressed in a very thorough way, and that is the procurement. I mean, we're talking about taxpayers' money here, so we have to find this rather peculiar instrumentation within companies who are A, used to do this, but probably B, not used to do it in the Middle East. So this is from time to time a tedious process, and the result that we achieved so far is for the X-ray source, we had a call for tender, it is evaluated, and we expect the contract to be placed soon. Call for tenders out with deadline for the submission before Christmas, before end of the year, concern the front-end components and the radiation safety hatches, because that is then the first thing that you need to install once you have the X-ray source in place. The computing hardware and the monochromators, there we prepare the call for tenders and expect them to go out in a matter of 1 to 3 weeks. The experimental equipment likewise, but probably a little bit later, let's say next year. And then, of course, the general infrastructure, what has to be done to prepare the floor, the ground for such a Beamline. It's not always called for tenders. This is in progress at SESAME. So this is where we stand. And here I want to, let's say, stop myself, hope to have laid the scene for those people who come after me. And I would just finish my presentation with an image of the ESRF in the morning skies, and to repeat the major message that I have today for you, the potential users, and that is that BEADS is made available for you, current and potential users from the SESAME members, but also from elsewhere. And please keep in mind that beats can serve you only if we have your valuable feedback and requirements and the needs during the process of building the Beamline, if possible already. So we can adapt ourselves to your needs and you learn what could be possible for your research at this facility. With this, I thank you very much for your kind attention. Thank you very much.
Thank you very much indeed, Axel, for this most informative introduction, exploring the project, its background, its current state. Are there any questions, comments, queries? Can I just check with my colleagues whether there are any questions in the chat? Any raised hands? Axel, your presentation was so clear that it left no questions. We can, of course, take further discussion and questions at a later point today, in the end of today's session. And of course, there is time to ponder topics for discussion, queries, and so on for tomorrow's breakout rooms, where you will be able to meet with Dr. Caprolat, together with Dr. Andrea Lausi, to talk about user policy, access, and so on. Are there questions at this point? Nope. So in that case, I suggest we thank Axel once more for this talk. Thank you very much indeed. And we move to the next speaker in our program. And this is, of course, Dr. Andrea Lausi, the scientific director of the SESAME synchrotron, where the BEATS beamline will be constructed. And in the way of introduction, Dr. Andrea Lausi is a steering committee member of the BEATS project, as well as leading the work package 6 beamline assembly and commissioning. And he got the laureate degree in physics at the University of Trieste in 1991, with a research focusing on phase transition in two-dimensional systems. Main scientific activity of Dr. Lausi is in the field of X-ray scattering, optics, and methods, including high-pressure powder diffraction, atomic X-ray holography, and diffuse scattering. And Andrea has extensive experience in the science programs of synchrotron light facilities, having worked at Elettra Synchrotron Trieste in Italy since 1996. And Dr. Andrea Lausi also has long-standing experience in science communication. He was a member of the communication task force of Elettra and the person responsible for the Elettra content. In April 2019, he was appointed chair of RISE. RISE stands for Research, Infrastructure, Communications, and Engagement. And this is a working group of the ERF AISBL, which stands for Association of European Level Research Infrastructure and Facilities. So it's my pleasure now to give the floor to Dr. Andrea Lausi, who will be talking to us about BEATS in the context of SESAME. Andrea, please.
Thank you, Kirsi. Thank you, everybody. Thank you to all the convenees, all the organizers. And what I must say also is that I am also the new scientific director of SESAME. I am here only since March. And I think that the word March tells you what I have encountered since I am here. in the very first days, I was already planning a physical visit to Qatar, which obviously could not have taken place until now. So really, really happy to be finally, at least virtually, with you. And what I will speak today is essentially, I will give you an introduction of what a synchrotron is, what a synchrotron source is now, and on something about the history and the status of SESAME in particular. So let me share my screen. And so in the first slide, what you see is the building of SESAME lying in the wonderful hills north of Amman. And this is the building which hosts the storage ring, which is SESAME. It is where we produce soft X-rays, hard X-rays, infrared radiation in order to study matter. So to make a bit of a history of these kind of facilities and of the use of X-rays, which has given so much insight about matter, we remember that these X-rays, these mysterious rays, were discovered much time ago, but in a very short time, science found also a way to use them, apart from some very first funny trial. I remember an article in 1907 about the color of X-rays. It was a German article of a scientist telling that it's blue, because if you put the eye to a tube producing X-rays, your eye at a certain point tells you that you are seeing something blue. Then most probably don't see much more for the rest of your life. So that was a field of research that was abandoned quite early. What is the color of X-rays? Instead, what went on quite long is the use of X-rays of various wavelengths, from soft X-rays to hard X-rays, to have informations about matter, positions of atoms, chemical nature of samples, and so on and so forth. And application after applications, this required brighter and brighter sources of radiation. So starting from the Coolidge tube, which every department of chemistry has in its basement, and every hospital has in his radiology departments, has brought X-rays everywhere in the world. But it has been also found out after the end of World War II that this radiation could have been produced also by moving electrons, accelerating electrons at a speed very near of the speed of light. And that the light produced in this way was much better in terms of many properties with respect to what you can do with the laboratory source. Accelerators were already there. They were built by physicists to explore colliders, to explore the subnatural, the inside of the nuclei. Well, then material scientists started use of these facilities, which was so successful that nucleated the use, the construction of dedicated machines. So in the 70s, the first synchrotron center started to be built for research, and this went through a process of development and which brought us to our present third and maybe fourth generation of facilities. So what are the things that make these kind of sources so special with respect to what you can have in a laboratory? many properties which are listed here in red with some comments, but essentially two of them: the wide spectrum, which is available, and the brilliance. By brilliance, I mean the number of photons which you can obtain per second per millimeter square of the source in a millirad squared of the beam divergence and per 0.1% of bandwidth. Complicated notion of brilliance, because it is a number, gives you a feeling already, it's a figure of merit which lets you understand more or less already, just looking at these characteristics of the source, more or less how many photons you will be able to have on a tiny spot in your sample at the end of the instrument that you construct to tame and to tailor this radiation to your experiment, which is the called beamline, of which we are speaking today as beads, for example. So, about the spectrum, as you see, the electromagnetic radiation that you can obtain from a synchrotron spans several decades and goes from microwaves through infrared, crosses the visible, which is that very tiny part of the spectrum, goes into ultraviolet, vacuum ultraviolet, soft X-ray, and up to hard X-rays in energy, or down in wavelengths to below the Armstrong. And this makes them exceptionally flexible sources. So you can build a ring, and depending on how you manage some details of the magnets that you put in there, you can obtain very different sources for the very different kind of experiment measurements. What to build then? Okay, it's a natural phenomenon after all. It's nothing. It's something which exists in nature. On the left of your screen, you now see the Crab nebulae as seen through a X-rays telescope, Chandra, and you see that the result of the explosion of the supernova which created the Crab nebula, there is a lot of charge which is running at the speed of light, which throws in our direction X-rays. Without being so dramatic and so far, we can build instead machines, facilities in which we keep electrons in orbit practically at the speed of light, 0.99999 and several 9%, depending on the energy, which could be goes normally between 1 and 6, 7 giga electron volts. You keep them in orbit, and then by being in orbit, as already Axel has remembered, at every curve they do emit electromagnetic radiation of various kind of wavelengths. So a synchrotron radiation facility nowadays is made in this way. You have a injection system, which can be a linear accelerator or a linear accelerator plus a booster, which is a real synchrotron. Synchrotron gets its name, it's an accelerating machine. It gets named by the fact that at every turn you increase the energy of the particle inside, which you are accelerating. If you do this, you obviously have also to increase the field of the magnets in order to keep the same orbit. So in order to keep the same orbit, you synchronically increase the magnets, hence the name synchrotron. So you either have a LINAC or a LINAC and booster, and from there you get bunches of electrons into a vacuum ring where actually you stop increasing the energy, but you just keep them in orbit. This is called a storage ring. 99% of the machines around are storage rings now. And these are polygonal objects, so straight sections, bending magnet, straight section, bending magnet, and they keep the electrons in orbit, in round orbit. At each bending magnet and along the path, at each other set of magnets, radiation will be emitted and will be collected and used for experiments. Which means that at every turn, these electrons will lose energy. So you need a radio frequency cavity which restores at every turn the energy of the electrons. So the name of the game is just to keep them in orbit and circulating them as long as possible at the speed of light. Okay, so the various kind of that you find in these machines define the kind of source that you have, and give you one of the stories of success of synchrotrons in the past 60 years, which is this always famous graph of the brightness versus time, the very famous Moore's law. Yeah? Moore's law is the history of success of modern industry, the number of transistors which double every 2 years. That is the green line. And on the other, on the left of it, you see the line which shows you how much the brilliance has been increased by building better and more performing rings and magnetic devices inside the rings during the past 60 years. So you see that going from X-ray tubes, which date, as you know, from much before, X-ray tubes are a very violent way of the X-rays. You know, you just smash electrons to a metal target and you shake up electrons. They return to their core positions by emitting X-rays. This goes in every direction. The brilliance is very limited. Then, instead, if you do, and that was the secret of success of the first uses, so the first generation, if you have a bending magnet where electrons are moving at the speed of light, you get a much, much higher brilliance. You go up by 12 orders of magnitude already. And this makes it already interesting to build machines and optimize them for this purpose. And so you get second generation machines, which synchrotrons which are built for producing X-rays. Then to go to the third generation, if you introduce between the bending magnets, in the straight sections between the bending magnets, set of zigzag magnets, which if the name of the game is make the electron bend, then you can build many bends one after the other. And in this way, you get a wiggler or an undulator. The wiggler will be simply the reproposition of the bending magnet effect several times. So you increase your intensity by the number of poles. If instead your undulation is very small, then you have interference between what is emitted at every zig and every zag, and in this way you get the key apparatus third generation source, which is a undulator, where the intensity is proportional to the square of the number of poles. Or you can do it even more and go to fourth generation machines with free electron lasers, in which you build an extremely long undulator, which then you are out of the paradigm of round machines. You just put a long undulator at the end of a linear accelerator. And in this way, you have the effect that from the beginning of the undulator, electrons start emitting. They travel at the speed of light, so which means that they travel together with the radiation they emit. And starting from thermal noise, then you have interference between the electron and the field emitted, and you have bunches which regulate themselves to be all in phase, and in this way you have a multiplication. So you have interference between the light emitted between two different electrons, and at the end you multiply by the square of the number of electrons in the bunch. But number of electrons in the bunch is 10 to the 10. So you squaring that number, you get an going from the synchrotron to free electron lasers. Okay, once you have built this machine, you are only halfway to the experiment. What you need to do is a beamline, that is the optical object which allows you to tame the radiation and tailor it to the experiment. So for in general, what you will have is something containing pipes with mirrors, monochromators, slit systems, shutters and stoppers for safety and for closing, all under vacuum, and bringing the beam down to the at the end. So what happens when you decide in your country or in your region to build a synchrotron, to build an instrument like this, which is, as I remembered, a very, very flexible machine. So the day you have finished, you obviously first build the machine. So the day you end the machine, you have a huge hole, empty, ready to host beamlines. And if you go on and on and on with this, you end up in a situation similar to this is the little synchrotron in Berkeley. And as you see, it is a totally crowded space with experimenters. So on beamline A, B, C, D, E, F, G, etc. You find people dealing with batteries, dealing with stress and strains of materials, dealing with cultural heritage samples, dealing with any kind of science, and they are so close. They do also interact day after on a daily basis. So what you have is really a mall, a cultural science center, evolves continuously and adapts to the scientific case around it. It's like in a way it's just like the market. The market is not made by the producers. The market is made by the consumers. So in our case, the synchrotron is not made by the beamline scientists. It is made by the users, as well as the synchrotrons. Inside the synchrotron, there is a community which interacts. The way synchrotrons interact between them, among them. And so since a few years now, it exists the League of European Accelerator-Based Sources, LEAPS. And SESAME is, since 2 years, the first associate member of this league. And you see the numbers around here. We are speaking of a community of 40,000 researchers all around Europe and also the Middle East, who to use this machine to produce their science. SESAME is a story of visionary people in this scenario, in this international thing. So I am somehow proud that it started in my hometown, Trieste, which maybe some of you know because of the International Center for Theoretical Physics. So, and this is where it actually, the interaction for the onset of this source in the Middle East started, with the first document signed, and then looking for a place, and then starting defining how the machine could have been done. The first thing was finding a place, and that was Jordan at the end, in this, as you have, in this magnificent place where I live, which is Allan, northeast of Amman. Yeah. So then the members, the members involved in the construction of SESAME are Pakistan, Iran, Palestine, Turkey, Cyprus, Israel, Jordan, and Egypt. They all joined forces in order to build this machine in a consortium, in an international institution which has been modeled after CERN. So we have members and we have also observers. The role of the observers is to help, to also to be sometimes economically involved, or to foster forces outside of the members. The original idea was, and this is something I want to stress out, because the story was beautiful, after all, that it stuck with us, that the German light source Bessie 1, which was a source built in the 80s, was to be disbanded, and German scientists proposed to use it to build SESAME. But this is not really a good idea, because you are not providing an up-to-date machine if you start from an old one. So this idea was abandoned, and Bessie 1, part of it was used for the injector, for the booster of SESAME. SESAME is a totally new third-generation light source and has been built only to be SESAME, not as a refurbishment of a previous machine. So, as being a synchrotron radiation source like the one which I have described before, now we can observe how it looks like in the map. So this is Linac and booster. Here we have the microtron and old part of the old Bessie 1, which is now completely refurbished and is our booster. From the booster, electrons are injected into the main ring, which is this one. These are the radio frequency cavities, and these are the bending magnets and the straight sections between bending magnets where you can put insertion devices. Yeah, you know, we physicists don't have much fantasy for names. So the general name for these devices, which you insert wigglers and undulators in the straight section between bending magnets, are called with the general name insertion devices. And so here you have the various beamlines. There is an infrared beamline, which is already operating, X-ray fluorescence, and X-ray absorption phase traction beamline already built, a material science powder diffraction beamline. Here will be beads. As you see, beads will be the longest instrument of SESAME, it's 40 meters, and HESEP is here, is coming soon as thank you, a soft X-rays installation, which will have also a Turkish branch line here. So there will be 2 beamlines here, actually. I will go through just a few images just to see you which kind of difficulties we had to address and how we overcame it and what it looks like in real life. So this is the radio. This is a mirror chamber being put in place. We are the only one, the only synchrotron which is completely powered by solar plant, and these are the phase 1 beam lines. Beats is among them. This is how we work. But of these second part, I will speak more tomorrow when I will introduce how to make a proposal and how to become a user. This is the current per day, and this is a show of the many proposals from the many countries that we receive every 6 months, 1 year, 1.5 years, depending on how much Corona is. But here we are already in the presentation of tomorrow. So I think that I stop here, and thank you very much. And we will check in again tomorrow, but with the procedure how to apply for beam time at SESAME.
Thank you very much indeed, Andrea. Of course, the presentation of Dr. Lausi tomorrow will be of direct interest to everyone who is wishing to use the BEATS beamline in the future, or indeed any of the other beamlines that are already operational at SESAME. So thank you for this talk, Dr. Lausi. Are there questions for Dr. Lausi at this point? Any questions in the chat? No? Anyone who would wish to comment or query at this point? I was very pleased to note in your table, while you're all thinking about whether you have questions or queries to Andrea, I was very pleased to note in the table for the beam times allocated, I think I noticed there Qatar, Andrea. Can you tell us a little bit more?
Yes, for the first time here, we had a request of beam time for XF measurements from Qatar, and the experiment has not yet been performed because of the status we are in now. It will be, I will explain it tomorrow, but we are now using what is called mail-in. So since users are not able to come because of restriction in traveling, they are sending samples. So wave after wave, we are inviting scientists to send us the samples, and then our beamline scientists, together at the phone or in Zoom conference with the users, measure them and go on.
I think, excuse me, I think the researcher from Qatar, she's joining us also this session. And she told me that she's looking to be personal because she has to do in situ some measurements, not by sending samples. So some of their hair samples should be prepared in situ. So.
Okay.
So that's why she's looking to do it hopefully by next March or sometime, which is something extra.
It will be March. We might be optimistic as I see it now, how the planet is behaving. Yeah. But yes, a certain amount of users will need to be here. Yeah, so there are not this mail-in process is not for everybody. It's not not everybody can accept to do it. Someone needs to be here because the preparation of the sample is sensible, and so yes, okay. If this is the case, even more, she will be most welcome to be here.
Yeah.
Thank you, Dr. Grauber, for this update, and it's really very pleasing to hear that there is growing interest from Qatar to use SESAME, this science facility, in our region. Are there other questions, comments, or queries at this point? We, of course, have the opportunity tomorrow to interact further with Dr. Lausi, as well as in today's question and answer and panel discussion session. So thank you very much indeed, Dr. Lausi, for this presentation. And we look forward to, of course, welcoming further future users from Qatar, both to BEATS and to SESAME in general. Now it's time to hear from the Beamline scientist of the BEATS Beamline, Dr. Gianluca Iori. Gianluca holds a MSc in Mechanical Engineering from the University of Bologna in Italy, and a PhD in Biomechanics from the Technical University of Berlin in Germany. From 2013 to 2014, he was a research fellow in computational bone mechanics at the Rizzoli Orthopedic Institute in Bologna. And between 2015 and 19, he was at the Berlin-Brandenburg School for Regenerative Therapies of Charité University for a PhD in osteoporosis prevention and diagnosis. His research focuses on imaging and on the mechanics of nature's materials, and was awarded with grants by the German Academic Exchange Service and by the Charité University Hospital of Berlin. And since January 2020, this year that is, he was appointed as Beamline scientist at SESAME, where he is coordinating the design and construction of BEATS, the Beamline for X-ray tomography of SESAME. And Dr. Iori today is going to talk to us about designing the BEATS tomography Beamline, its construction and future operation. Gianluca, floor is all yours.
Thank you, attendees of today.
There seems to be a problem with the internet connection. We can hear you now. It's a little improved. Let's try to see if yes, now it's better. But apologies if I interrupt you at some point, Gianluca, in case there is a problem with the internet connection. Let's try again. Now it sounds a little bit better. Please do go ahead, Gianluca. Okay, Gianluca is writing that he can't hear, so he will try to reconnect. And while he is doing that.
I think the problem is with my bandwidth, because when I share my screen,
Can you hear us, Gianluca? One option, of course, if Mr. Angela, do you have Gianluca's presentation? If we show it from here, and then Gianluca joins with the voice only. We can hear you, Gianluca.
Maybe one of them turn off the camera.
Yes, let's try, Gianluca. One set of options we could, of course, try with your new connection. Gianluca, what about trying option 1, which is if you turn off your video but share your screen only? We could try this one if your bandwidth can carry it. And the second option is if you wish to email your presentation to Mr. Angelos or Simona Lemos, who can pass it on, and then we could just hear your voice. Let us try that. This is, of course, something that we all live through these days of the pandemic, that we are very reliant on local bandwidth and so on. So do please give us a moment to try to help Gianluca to be able to give his presentation. And in the meantime, when we are arranging things, may I ask kindly if Dr. Alexander Ruck could be standby in case there is a continuing problem with Dr. Iori's presentation, the bandwidth, so we could swap things around. So let us take a moment to see if we can get back on track.
Hello
with,
again.
Hello.
I will try
Hi,
now. Hi, sorry for this. Every day we are changing rooms due to the COVID regulations, so the test that I did yesterday doesn't apply to today's connection. So I'll try again.
Okay, fingers crossed.
What about now?
It's much better. So let's try if this works.
Okay.
Everyone here.
So I'll wrap up the introduction. Sorry for the interruption. After the first two talks by Axel and Andrea, I'll go more in depth towards the principles of computed tomography and the technical design of beads. So this is a layout of the building of SESAME. This is the north side where beads will be installed. And as you can see, we will use one of the longest straight sections that are available in the building. Beads will be installed on a straight section of the ring, and it will be 45 meters long to exploit long propagation distance, so to look at our source from as far as possible. We will quickly see why this is important. This is a general layout of the beamline. It is divided in 4 parts. From the left, there is a part called front end inside the storage ring of the accelerator. There is then a small optics hatch where optical components are hosted. And then there is a long shielded pipe bringing the X-ray to another shielded hatch where the experiment takes place, which is the BIT experimental hatch. And this is also a layout of the beamline, more let's say a functional layout. We have again the wall of the SESAME storage ring here in the middle, what is on the left is inside the tunnel. So it's something that as users you probably won't see. It's called front end. We have a fixed mask. We have primary slits and filters to tailor the size and the properties of the beam. DMM stands for double multi-layer monochromator, which is a system of two crystals reflecting the beam for energy selection. And then on the right, from 33 to 45 meters from source, we have our experiment. So from this layout, you can already see that the Beamline has been designed to allow two different modes of operation. There is what is illustrated as pink is our white beam or pink beam option when the mirrors of the monochromator are out of the way. So we allow the full flux to travel to the experiment. This is for a high speed and high flux experiment, large dense samples, for example. When we want energy resolution, we insert the monochromator and we work with one single energy, so monochromatic beam for energy resolution and more experiments requiring a higher like an energy selection. The source of the Beamline, this has been introduced by my colleague Axel already. Just a few words. It was decided already in 2019 to go for a wavelength shifter or superband concept. The decision for a 3-pole wiggler was taken in September last year. The reason is explained in this slide. So this is a simulation of the photon flux we obtained with a 3-pole wiggler, such a device, a 3 Tesla 3-pole wiggler. The comparison bit is in orange in this plot. The comparison is done with the beamlines that are sitting on a bending magnet. So you can see that we can exploit a much broader spectrum, particularly with the photon energies that are not limited to 20 or 30 kiloelectron volt, but we can go up to 50 kiloelectron volt. This has a direct impact on the scientific case because it allows us to access higher energies, allow us to access a broader variety of samples, more dense and larger samples. Now, very quickly on the principles of computed tomography. This is the first CT scanner that was introduced in a hospital in the UK in 1971. So CT computed tomography was introduced in the clinics for imaging of the human body. How a beamline for tomography at a modern synchrotron facility looks like is actually very different. This is a picture of Tomcat at the Swiss Light Source, where I'm sitting now for a training. This is the experimental hatch of Tomcat. So we have the beam entering from the left side of the figure. The X-rays are traveling here in the middle of the figure through the sample, which is positioned on a rotation stage, so the sample can rotate. And then they are intercepted by a microscope, which is sitting here behind the sample. From this diagram, we see what happens. The X-rays are passing through the sample and they are intercepted by a scintillator, by a thin foil, scintillating foil, which converts the X-ray to visible light. The visible light is then magnified by a microscope objective eventually and then hits the screen of a detector, a CCD. In this diagram, it will be a CMOS detector in our case. This procedure is applied for all possible angles, 180 or 360 degrees, depending on the scan. And the result for each row of the detector is a figure like this. This is called sinogram, which is the detector response for all 180 degrees of orientation. These images are then processed by a computer that does the tomographic reconstruction, applies the radon transform, and from this we obtain slices and a pack of slices, in fact, which give us the 3D geometry, internal geometry of the sample. One of the techniques that we would like to apply at BEATS, and this is why tomography at a synchrotron facility becomes very interesting, is the possibility to enhance the contrast of light elements thanks to phase contrast. So this diagram from a book from Phil Wilmot explains how phase contrast is achieved. From the left, we have the X-rays. They are hitting some disks of different materials. You see that we have only 2 disks that are dark, so they are dense, and the rest are 1, 2, 3, 4, 5 disks of that are transparent, so very light materials that do not attenuate the X-ray. So when we put the detector right after these disks, you see that we have high contrast only for the 2 dense materials, whereas for the rest, we hardly see the shadow of the transparent disks. However, when we let light propagate further by taking the detector further away from the image plane, further away from the disks, we have that the edges of the materials are enhanced to Fresnel diffraction of those edges. When we bring the detector too far, we enter a Fraunhofer diffraction regime where we do not distinguish the shape anymore of the original object, only an interference pattern. So what we do in tomography is to stay in this regime, in the Fresnel regime, and enhance the edges of our objects by letting the X-ray propagate after passing through the sample. And this is actually the result of this technique and how it can be applied. This is a zebrafish embryo, so a 3D object which is composed of very light materials with atomic density very close to that of water, in fact. And you see that in the radiographic images, in the projections, which is the first row of this image, we barely see something. What we see is actually only these 2 little dark spots, which are the ear stones. So these are the only dense parts of the sample. The second and the third row are 3D reconstructions. So these are already slices through 3D volumes. The second row is a reconstruction done in absorption. The third row is a reconstruction done with phase retrieval. So you see that going from the left to the right, when we increase the propagation distance from the second row, we enhance the edges of the different phases of the embryo. When we applied phase reconstruction, so phase retrieval, we're not sensitive anymore to the attenuation of the X-ray, but to the phase shift due to the passage of X-rays through different phases of the sample. And we can boost very much the contrast of different parts of the embryo. Now, one of the conditions to apply phase retrieval and to enhance these edges is to have sharp edges. And this is something we all have, how to say, a common experience of from when you look at the shadow of your hand as illuminated by the sun or by a light bulb. You know that the edges are more or less sharp, the edges of that shadow, depending on the relative size between the source of illumination, object, and detector, or the wall where you project the shadow, but also depend on the size of the source. So we need a very small source, or as small as possible source, to have a sharp edge without blurring of the edge. And the source size at the synchrotron facility mainly depends on the properties of the storage ring. So how well you can confine the electrons in the ring while they circulate. For beads, the distance from source is comparable to that of other beamlines for tomography, but the X-ray source is not. So we have to act on this. And And the way we will do, if we look again at the layout of the beamline, is by introducing slits in the front end, which is just an aperture that we can close to tailor the effective source size. So we create a secondary source with a reduced size down to 0.5 millimeter, through which we can look at samples and apply phase contrast. So going back to the possible modalities of operation, we have now a mode 1, let's say white beam, and mode 2 monochromatic beam for experiments requiring high flux or energy sensitivity. But we can then operate also using absorption, so with high flux, slits open, or for high sensitivity and phase contrast by closing the primary slits and creating a secondary source with a small size. Very quickly, the equipment of the beamline, which is what we are designing and procuring right now, the front end is, as I mentioned, is there to safeguard the experiment, to define the beam size and properties. So we have SESAME and Electra right now designing the fixed mask, for example. This is the aperture that defines how much the fan of radiation that is allowed through the beamline. We have ALBA and ESRF together with SESAME designing the hatches for the optics and for the experiment. And then we have the ESRF helping on the design of attenuator systems and of the primary slits. For example, this is a picture from the slits of ID19. We will have the pleasure and the honor at BEATS to install the recently exchanged and refurbished ID19 slits of the SRF. So back to the layout. This is a slide on the double multilayer monochromator. It's a picture from Tomcat, which is inspiring our design. This is a system with 2 crystals, 1 and 2, where the beam is reflected to select an energy between 8 and 50 kiloelectron volt. The way it works is that by changing the angle at which the beam is reflected, one can select, thanks to Bragg's law, an energy in this range, 80 to 50 kiloelectron volts. So the 2 crystals are moving in space up to 1 to 2 meters of excursion. Once we reach the experimental hatch, which is the part that you will visit as users, hopefully, we have a first system of slits and alignment provisions to align the sample in the beam. We then have a pipe bringing the beam again to the sample position, where we have a tomographic sample stage, and then a table with microscopes and a beam stop. The size of the beam for the experiment can be changed by bringing the sample up and down the hatch. So you see that from around 40 millimeters of beam at the entrance of the hatch, we can exploit up to 50. We are trying to bring this to 70 millimeters at the end of the hatch, so to illuminate larger samples. The sample stage is a device from which our colleagues at the SRF have a lot of experience. Is a high precision and heavy duty sample stage. You see here 2 images from the SRF, from BM5 and ID19 at the SRF. The important thing here is that it must be the system must be very rigid and allow us to prepare stack of samples like this to automate, like the one you see here on the bottom right, to automate the scanning of a series of samples without interrupting the procedure and entering again the hatch. We then have a detector stage, which is again inspired by a solution from the SRF. On the right is the detector stage of ID15 we are inspiring from. And on the left, the mechanical design of the detector stage that we are actually developing. As you see, it can host 2 detectors for different magnifications. So there is a high resolution detector on the left with 2 different objectives, and the lower magnification one on the right. And the cameras are 2 identical cameras, also very well established and proved at the SRF, which are scientific CMOS cameras. So with this portfolio of detectors, we will be able to provide different magnifications. So different magnifications means different resolutions at which we can scan, and also different field of view, so sizes of samples that we can possibly see. And from 1-fold to 10-fold magnification, which is what we aim at installing, you can see that we will go from large samples up to 15 millimeters in size with a pixel size of 6 micron, 6.5, down to samples of 1 or 2 millimeters with the sub-micron resolution, which gives us a rather versatile portfolio of detectors that can be used in combination. Finally, some words on how we can actually perform in situ studies. So we are considering the installation of a mechanical rig for mechanical tests. This is an example from the APS, I believe. It's a simple system that allows to compress and pull samples. This is very interesting, for example, for the analysis of biological samples under mechanical load, but also plastic foams or other polymers, how they deform during load, or for example, 3D printed materials or lightweight materials like metal foams and so forth. Another sample environment is a furnace for in situ heating. This is an example we are trying to replicate from the SRF. Is a furnace that can go up to 1500 degrees Celsius and can be used to study, for example, the evolution and phase transition of composite materials during heating. Generally, at this part of the presentation, one would explain what the tremendous infrastructure for data acquisition and data processing behind such experiment would look like. But for this, we are lucky, we will have a specific talk tomorrow morning at 10 from my colleague, Dr. Charalambos Chrysostomou, who is the leader of the work package 7 of BEATS, dedicated to the design and the installation of computing infrastructure for data acquisition, processing, and storage. So don't miss the talk tomorrow by Dr. Chrysostomou. Without spoiling that talk, what I want to mention, and I conclude here, is that we will provide the users with a set of software, mainly open source, for 3D data analysis and processing. One very interesting thing that can be generated with high resolution and high quality 3D data is numerical simulations for solid mechanics or fluid or gas dynamics, for example. This is the plot. The figure shows an example from a bone sample that was scanned with the synchrotron CT. It was first of all segmented and prepared to simulate the response of this tissue under mechanical compression. So this is where the user, the role of the user becomes very important. If you have a particular expertise, a particular requirement, we would be happy to collaborate to establish a pipeline for the generation of such numerical simulations, and we hope we can collaborate in the next years. So I think the next talk from Alexander Rack from Dr. Rack will cover all the potential scientific application of this experiment. And with this, I would like to thank you, and sorry for the initial complications.
Thank you very much indeed, Dr. Yori. It's really a pleasure to hear from you in terms of the progress, the design of the beamline, and we're very happy that the initial hiccups and so on could be sorted out. Apologies also for some technical issues. I understand that there was some echo during the presentation, so we apologize for that. We are looking into it just to make sure that it does not appear again. But nevertheless, I hope that you were able to hear the presentation content. Are there any questions to Gianluca at this point?
Yes, I would like to ask a
Do
question.
we have any questions on the chat? Do go ahead.
Yes, thank you. I want to ask you regarding the payload of the moving stage and
Yes.
the accuracy of the movement for the stage and the range for the z-axis, and also for the rotating, the accuracy of the rotation and the speed of the rotation for the moving stage.
Yeah, so the speed and the accuracy are a compromise with the resolution that we want to achieve. So the resolution in terms of imaging will be around 1 micron or sub-micron, which is also the resolution we have to achieve with the rotating stage in order to have an image free from movement artifacts. Or the vertical stroke is half meter in this design. So it's as you saw in the picture where there was this pile, the stack of rocks, it can be actually very tall, the sample size. We can scan a taller sample by performing a stack of scans. The payload. There are the factory, the supplier we are discussing with provides different versions. I hope we can have a limit around 25 kilograms. So quite stable and stiff in order to also mount sample stages on top. In situ stages on top.
And also I want to ask you regarding the rotation speed and the accuracy. Yeah.
So it's up to actually 1 hertz. So as you know, then comes the limitation in terms of how fast we can image, because we cannot do one tomography scan in 1 second with the detectors we have. The detectors are limited to 100 frames per second when you acquire with a full frame, which means that to acquire 1,000 or 2,000 projections, you will never perform 1 rotation in less than 10 seconds, 20 seconds, right? So the scan speed and rotation speed is very much function of how dense the sample is, if you illuminate it with the full white beam or a monochromatic beam and so forth.
I also want to ask you, for the beamline, is it only monochromator, or you can like adjust the setting, for example, to use pink beam tomography?
No,
like
pink beam is the first thing we will. I'm sorry if this if you couldn't hear well the presentation, pink beam is possible.
Thank you very much.
Yeah, thank you for the questions.
Questions? Any further questions or comments for Jean-Luc at this point? If not, then let us take a brief break. So you may catch a cup of coffee or tea. Unfortunately, in these online occasions, we can't offer any refreshments, but I hope you are in a location where you can refresh yourself a little bit. So we would like to suggest a break of 5 minutes, not too long, not too short, hopefully. If there is a need for a longer break, do let us know now. So we reconvene around 6 past 11. So 5 minutes break now. Thank you very much. Hi, welcome back to the second part of today's event. We now have the pleasure of hearing from Dr. Alexander Rack, who I would like to briefly introduce to you now. He studied physics at the Technical University of Berlin and received his degree from the same university, doctorate, in 2006 from the Department of Materials Processing. For the latter, he received the Ernst Eckhard Koch Prize of the Bessie-II synchrotron light source, which was, of course, located in Berlin, Germany in 2008. And for his first postdoc position, he joined the Anker synchrotron light source in Karlsruhe in Germany, where he was in charge of synchrotron instrumentation for hard X-ray microimaging. In 2008, he moved to France to work at the European Synchrotron Radiation Facility in Grenoble. Initially working at the microdiffraction and microscopy beamline, he soon joined the microtomography beamline, ID19, which is heading as responsible beamline scientist since 2016. Present research interests are the study of time results phenomena by means of ultra-fast hard X-ray imaging, which includes shock and crack propagation in dense matter, as well as materials processing, such as additive manufacturing. Since 2016, he is Deputy Group Head of the Structure of Materials Group of the ESRF. And Dr. Rack will today talk to us about synchrotron-based hard X-ray microtomography at BEATS, potential future applications in Qatar. Dr. Rack, floor is all yours. Dr. Rack, can you hear us? Alexander?
I hear something,
he's writing in the
but it's...
Yes, we can hear you. Please feel free to start.
So you hear me clearly? You can hear me clearly, yes?
Absolutely.
Okay, then I just start because
Loud and clear.
Perfect. Okay, and welcome to the nice introduction, which I couldn't hear, but I can imagine. Thanks for giving me this presentation here, the chance to present. Also, another sorry that I cannot remove the mask, but that's part of the confinement rules here in France. I hope you still understand me anyway. Based on the excellent talk I had from my previous colleagues, I will, in the next 25 minutes, speak a little bit about applications when using synchrotron radiation for hard X-ray imaging, especially for microtomography, and also, of course, with the hope to inspire a little bit future applications from you as a user of this beautiful device we are installing at the SESAME light source. So when we go back to the talk which Jean-Luc just gave to us, there was a lot of mentioning of new terms probably for you, such as phase contrast. I'm very happy he went already to all the theory explaining that. I have now the pleasure more to show you some nice examples what that means in reality. So, for example, why we come to a synchrotron, what is a nice goodie. So usually I start with a nice picture. This is already synchrotron data. Explicitly, I like to say this is not ESF data. So many of my examples I choose are taken from other light sources, just to show that basically what we are going to present here is also something which you will be able to do at the SESAME light source at the BEATS beamline. This is a mosquito. That's an image at hard X-rays. That's already a nice example for a synchrotron application. Why? Well, the mosquito here is fully unstained. That's fresh organism, and we see it with hard X-rays. Why? We can see it not because of a shadowgraphy, which we are used from classical X-ray imaging. This is because we have refraction at interfaces. I hope you see my mouse cursor. Nevertheless, when you look around the objects, you have everywhere this white halo. This is what Jean-Luc introduced to you as X-ray phase contrast, and that makes imaging at a synchrotron light source very sensitive to find details. Yeah. The other thing is, of course, we get high resolution, and that means we already goes on that one, and that's another advantage of using phase contrast. The phase contrast basically is not based on absorption, so even if you put a lot of photons on your sample, it doesn't necessarily mean you choose. As a reminder, this is so enough very fast images. So this is a few images per second, and that's all efficient, for example, to make an in vivo study, which is extremely nice for some otherwise. Organs, for example, you have to freeze dry it, so basically you damage it, yeah, or you have to cut it in whatever way. A powerful approach. And it was not so fast. And again, the data from the Anker light source in Germany, light source which has similar specs than the SESAME light source. Again, phase contrast, I would use that one more time, or strengthen one more contrast when using a synchrotron light source for X-ray imaging. Phase contrast is really a magic. On the left, this is a materials research. This is an aluminium magnesium alloy tomography. Basically, we don't see anything besides a bit of noise. Yeah, and then the phase contrast that is from light source is that you just move your detector a little bit away. You know, we are moving from 2 centimeters to 10. And please say that helps you a completely richer setup. So suddenly we make the invisible visible by refraction on interfaces. So in this case, we see different material phases very nicely. Why we see them? Again, because we have refraction at interfaces. Yeah? And phase contrast is also nice if you want to go up a bit more in speed, because even if you have a very noisy picture, still the eye is very good to discriminate these refraction interface I mentioned before. So quickly, we had already an introduction what is tomography all about. The synchrotron, basically, the main difference is compared to the medical scanner that we rotate the sample and not the source like in a medical scanner. That can be a constraint. You know, if you want to do fast acquisition, you have to be also able to rotate your sample very fast. So in most of the cases I'm going to show you, that's rather static example. So what we see here is raw data acquired at the Bessie light source. So that's on the left. These are radiographic projections from a mouse jawbone. What we see here is already quite high resolution data. As a mouth, you can imagine it's a small head, so even a smaller jawbone and very tiny teeth. And despite in this basically small object, we see a lot of fine structure. We see the teeth, we see the root structures, the bone. It means we acquire maybe 1,000 to maybe 2 samples of view from the same sample by rotating. Then get what we call the sinogram. If I take one line from that detector, from projection data, the sinogram real space image. Is that numbers what's happening. You take line by line, data back to the slide 1,000 that's taken for projection. So previously was not in it's visible through the screen. You see even very tiny here an interface, so that's the soft tissue, and here's the embedding material. So even that we are resolving. That gives you a flavor, and the big contrast here, these are obviously porosities, and then here we have bone. Yeah. And if you
Dr. Rack, Alexandra, can you hear us? It seems that we have lost the sound. Alexander, can everyone else hear Alexander? We cannot hear here, and I can see Andrea noting that he cannot hear. Alexander, there seems to be a bandwidth issue, connection issue at Dr. Rack's end. Alexander, can you hear us? So due to low bandwidth, local computer conditions at Dr. Rack's end, there seems to be a problem. So when the conditions improve, the notification here shows that we should be able to continue. Dr. Rack, can you hear us?
It's good to turn off the camera, keep the mic on.
Yes. So suggestion could be if you can turn off your video to reduce the load on the bandwidth and keep the presentation on, and of course the volume. Let us try this way if it would work. These are, of course, some of the issues that we live through in these days of the pandemic. Attempting to connect and communicate is always conditional for local conditions in terms of bandwidth. Dr. Rack, can you hear us?
Now I can hear you.
We cannot hear you for the moment.
Can you hear me?
Ah, very good. Yes, we do hear you, and we see your presentation. Would you like to please continue? Let's try without the video. I'm sorry, we cannot see you.
It's okay, you know my face now. Okay. So I don't know when the last time you heard me. I was telling you that basically when we have stacks of slices, we enter those stacks of slices into our rendering software. And I hope if I go forward and back in my video, up, yeah. Then basically we get a volume image. For us, a volume image is a virtual image of the mass distribution inside a sample. And again, at a synchrotron, widely non-destructive, high resolution and high contrast. Yeah. That was the introduction part on the tomographic technique itself. Yeah. An important aspect again is the phase contrast technique, because that's really the boosting in terms of contrast. Yeah. My personal belief is if you come to a synchrotron light source, then it's not necessarily about highest resolution. Laboratory sources give you also high resolution nowadays. The big thing on a synchrotron light source is contrast, and for us the name of the game is phase contrast. Yeah? So if I take again the example of the mosquito, with whom I started my presentation. Yeah? On the left, we basically see already a beautiful pictures. Is what we call the inline X-ray phase contrast, where we see nicely the interfaces. What I already showed you on the very first slide, which is very nice. And for example, if you want to do a visualization, this is very powerful because the human eye is very strong in identifying interfaces in the picture. Nevertheless, for image processing can be complicated, and there are things like face retrieval, which is on the right side. Again, for you as a user, it's not important to know the mathematics behind, just to know that it exists. So basically, by one more image processing step, we can boost the contrast even further towards this picture. And the advantage is, if you have, when you look on the bottom right, on such a tomographic slice reconstructed after face retrieval, that's very easy later than to process with the software, as I mentioned. For example, to do high resolution 3D rendering like that. So then you have basically the full mosquito head, and that's something which is very powerful and again very important. It's robust technique. It's almost out of the box. Yeah. Again, as wrapping up, why it's beneficial to go for synchrotron light to do X-ray imaging. What are our advantages compared to laboratory-based sources? Is the higher contrast. Narrow bandwidth means also less beam hardening. We usually use a quasi-parallel beam for imaging. It makes usually also the reconstruction quality better, and especially we have the phase contrast as the excellent sensitivity. I don't want just not only to make highlight of synchrotron, of course. The drawbacks are, one, it's usually more expensive. Okay, for you that doesn't matter, because for you as a user, usually the access to the beam time is for free, because you will go through a proposal system, so that's doesn't matter, but in the end it will matter the taxpayer. And of course the amount of beam time is limited. So if you have the idea to scan 1,000 samples for statistic relevance, then you might have a conflict with the amount of beam time available. But again, if you go now through a few other samples, if you keep in mind the excellent contrast, which I found important, and you can do beautiful things out of the box at a synchrotron light. So this is more materials research example. This is a carbon fiber reinforced silicon carbide ceramic. It's something which, for example, Porsche uses for the brakes. It's a high heat load material. What we see on the left is a tomographic slice. This is again data from Bessie, from the light source in Berlin. You see again very rich contrast. Also we have in black the carbon error, we have in gray the silicon, and the interfaces we have silicon carbide, which was just formed. There's roughly 4 micron resolution, and then you can do even a zoom in, and then basically you see even cracks inside the material, which happens during manufacturing. This is all synchrotron data, again high contrast. Just as a reminder, at a synchrotron, especially at the SESAME light source, there is not only the Beats beamline, there are also other beamline like the infrared and the fluorescence beamline, and of course there are also other possibilities to do correlative studies. I think then X-ray imaging becomes even more powerful, because you can non-destructively do many investigations. For example, this is from Bessie. This is a piece of pergament where basically they analyzed what is written there and with which material it was written. I have to admit, due to the breaks, I'm lost a little bit how much time I have left. I think it's roughly 10 minutes. I would, after we basically went now through the goodies of the advantages of using a synchrotron for X-ray imaging, I would like to show a few more detailed examples, also making you a bit more sensitive what can be done on a synchrotron light source or not. X-ray imaging itself is a wide field, which I would like to depict with these slides. Of course, there's a lot of things done for inspection. Nevertheless, Beamline, as I said, beam time is limited, so you are not basically doing high throughput inspections for industry. Life science is a very rich topic. Everywhere where you use microscopy, basically you can also use a synchrotron microtomography, because we are basically a 3-dimensional non-destructive microscope. Same for materials characterization, studying novel materials. Non-destructive testing, of course, would be interesting, but typically you don't do big objects at a synchrotron because the beam size is limited. Medical applications partially only possible because one of the things, indeed, I always say non-destructive, but the dose we can put on the sample is rather tremendous. So, for example, we are far away from basically doing. So the beam we are put on the sample is life-endangering. So this dose is really something to keep in mind. Further examples from which I collected just to hopefully to inspire a little bit. One is from the biomedical materials research, is bone regeneration and recovery of defects. Why? Well, if you have large-scale defects in the bone, there's basically the need to repair it. The standard solutions, either for that's something what probably every day happens to someone, is for teeth, bone implants, which are combined with bone regeneration materials to make sure you have enough you have bone to hold the implant. And then there are even larger cases, basically when you have a cancer treatment where huge pieces of bone need to be replaced. and the gold standard here up to now is usually bone transplantation. I don't know about the treatment here on the right on the school. I had once a bone regeneration approach just for teeth, and I can tell you that was not a very pleasant exercise. So I personally was quite interested to figure out how to improve that. Yeah. One big field by medical application and materials research are, for example, dental implants, which we studied at a synchrotron, again at the Bessie light source. Just a quick overview: in modern dental implant is made of usually nowadays on several pieces. Usually you have the main implant, which is inserted into the defect. Then you give it a healing period of a few months, and only then you start to enter other pieces, which basically then allow you to build up a crown. And the crucial thing is for the implant industry is this interface between the abutment and the implant, which can be a source for microbacterial leakage into the interior of the implant, which can then be a risk for an inflammation. And there are almost religious discussions in the implant industry. What is the best interface between to make that leak tight? Should it be a butt joint or should it be conical? Well, and the nice thing is, again, with a synchrotron, because we have this excellent contrast. If we do an image of such an implant, we see even very, very tiny interfaces, because that's again what we mentioned in the beginning, because we have the phase contrast. So we did a lot of studies comparing different implants design, and showing to industry where in their design can be weak points, where they have gaps between the different pieces, which could be a reason or not for microbacterial leakage into the interior of the implant, which is a very important case. Bone research, that's an example from the Advanced Light Source. That's a facility in San Francisco, also with similar sizes than the SESAME light source. Bone research, again, what I said already, the dose we put normally to the sample is quite high, but basically if you do properly your dose management, you can do bone research, and then you can beautifully also here visualize cracks. That's a bit older data, and again, cracks, why they are nice to visualize. We have phase contrast, and we see the interfaces very nicely. An example for the regeneration of bone is what happens nowadays if you have a defect in a bone and you don't want to make a bone transplantation, is you use bioceramic materials. What happens inside a bony defect when you put these particles like tricalcium phosphates, they basically decompose very slowly, so they prevent the soft tissue to grow into the defect. And while they decompose, they set minerals free, which the bone needs to form. That's like a modern approach for bone regeneration, which works very nicely. And there's a lot of things to study. As on the right, this is data again from the Bessie light source. We see this bone regeneration particle. This is actually a very nice picture, because you see a lot of particles. That was also very clear for those people who developed these materials that is a very bad bioceramic material, because 3 months after implementation, there was almost no new fresh bone. Basically, all the particles were still there. That, for example, means they decompose much too slow. And why, again, here you need a synchrotron? Well, people here need a nice contrast again between medical stuff. The goal is that people as a
Alexander, there seems to be a problem with the bandwidth and the sound. We can hear you now properly.
So you hear me or you don't hear me?
Can you hear us? We hear you now.
Peace. Okay.
So
I say
there was
something.
a few
should I just
moments
continue?
when there was a problem with the sound, but not very long. So I suggest that you simply continue. Thank you very much.
Okay, good. Sorry for that. Also what I wanted to show with this slide is that in materials research we have a lot of dynamics which are not very fast. So basically also at the beats beamline where we can do tomography rather rapid, maybe not fast but rapid. You can track dynamics in 3 dimensions. For example, if you take a raw material like a rock or like a magma, put it in the furnace and heat it up and do a temperature ramp, and then you do tomography at specific time points, you can track dynamics in 3 dimensions. Other examples for heat treatment can be the crack propagation inside a material. Again, here basically also the beamline will need your input as a user. Usually the beamline will provide you the excellent synchrotron imaging facility. And then of course it's to some extent would be also nice if the user come up with ideas. This is a nice example again from the advanced light source. I think this is basically a joint project where the synchrotron offers the beam time and the imaging capabilities, and where the user basically came up with that furnace to do the very sophisticated experiment. Last example from materials research. This is again BESI data. What is nowadays fashion is to look on batteries. Also here tomography at the synchrotron at higher energies is very interesting. Why? Well, on the left we see a slide through a commercial battery. Contrast gives you the steel housing, the manganese ring, the zinc powder. On the right, basically, we see a false colored picture. Nice thing again is when you have high contrast, you can do a beautiful segmentation on all these, and then you can study, for example, the powder decomposition with time. Don't need very high time resolution when you discharge a battery. This is all work done very successfully as a BESI light source at the moment with hard X-rays, with tomography, to study batteries and fuel cells. And that, of course, is, as you can imagine, at the moment, a very hot topic in the field. Well, and I think, with that, I would probably rather finish my presentation. I thank you for your attention. I'm sorry for all the technical problems. We did a test yesterday and that worked fine. I still hope I have time, and I still hope I can hear some of your questions. Thank you very much.
Thank you very much indeed, Alexander. And of course, we naturally understand the bandwidth issues, and we're very happy that we could hear your presentation to the end. At this time with the pandemic and the online communications, there are always challenges, but thank you very much for persevering through it. And we I think benefited from your presentation very much. In this moment, could I please check if there are any questions on the chat for Alexander? If not, and you are of course very welcome to simply voice your question if anyone has a question now. We also have an opportunity, and you have an opportunity to further interact with Alexander during the panel discussion today, as well as tomorrow in the breakout. sessions, in the breakout room sessions. Any questions? Thank you very much indeed, Alexander, for this wide-ranging presentation on the applications. I will now pass on to my colleague, Dr. Simona Lammers, for introducing the next speaker.
Yes, thank you very much. So yeah, indeed, I would like to announce the next speaker, which is Dr. Casey Laurent. She's the BEAT Steering Committee Vice Chair, and she's a faculty here at the Cyprus Institute. Furthermore, she's the principal investigator of the Biomera platform. Biomera standing for a Platform for Biosciences and Human Health in Cyprus, micro-CT enabled and synchrotron radiation enabled analysis. She's also the chair of the LAMP, which stands for Light Sources for Africa, the Americas, Asia, Middle East, and the Pacific. And her personal research focuses on human health and disease in the past through bioarchaeological approaches and paleopathology, as well as synchrotron radiation-enabled studies. So her talk will be titled Science Applications with Synchrotron Computed Tomography at BEAT and How to Become a Future User from Qatar. So the floor is yours, Kirsten.
Thank you very much indeed, Simona. And thank you again for this opportunity to interact with all of you from Qatar. It's really a pleasure to explore how you can access BEAT, tomography, Beamline, how you can become a future user from Qatar. And BEAT science applications are, of course, very wide-ranging. Anything that benefits from exploration of internal structures in great detail can benefit from this, any material samples. And here are some examples that we particularly focused on in the BEAT scientific case document, but by no means are these the only applications that we foresee. So archaeology and cultural heritage, health biology and food sciences, material sciences and engineering, geology and environment, as well as a number of applications within industry, the private sector are envisaged, but beyond this, we expect further applications. This slide shows some of those domains in more detail that we elaborated on, and of course, my colleagues from the BEAT project have also mentioned a number of applications. What I would like to stress at this point is if you don't see your particular research domain in these slides, that does not mean that BEAT is not accessible to you or relevant to you. As I mentioned, any type of material samples, as long as there is a valid research question that cannot be answered in a laboratory context, is relevant for exploration using the tomography Beamline BEATs. So do please feel free to contact any of us to discuss these potential applications further. I will now talk a little bit about cultural heritage and archaeology, a domain where I am active. Here are some of the UNESCO World Heritage Sites from the SESAME members, as well as, of course, from Qatar, Al-Zubarah, a very important UNESCO World Heritage Site located in Qatar. Cultural heritage sites have produced and are producing multiple types of materials and remains that can benefit from tomography and synchrotron radiation source tomography in particular. Here, we will today briefly look at archaeological materials. I will give you some examples, some case studies, showcasing some of these applications for particular materials ranging from manuscripts to faience, textiles, as well as artifacts of unknown materials. And this is, of course, very important when we look at the structures, the microstructures, the histology of particular unknown materials. We can then start making headway into what material there might be. And this is, of course, relevant in other contexts as well. We'll also look at biological remains from the past, whether they are human, plant, or animal. And here, just in a nutshell, the SR micro-CT on material remains from the past can really answer key questions in the region, whether it is about beginnings of agriculture, looking at particular types of plant remains, cultivars, domestication, or whether it is looking at technological advancement, looking at particular types of artifacts, their manufacturing, and so on, or indeed the people who were the movers and shakers in the past who created those archaeological remains, the people themselves, looking at their health and disease conditions, pathologies, aspects that are affected by our life histories. So here are some of the images just to bring home the type of materials and the range of it. Let's go to the case studies. Here, we're focusing on looking at artifacts of unknown materials. On item C there, you can see some pendants, some beads, if you like, of unknown material. They may be faience, and of course, faience at an early period, in the Chalcolithic, approximately 5,000 years ago, is very interesting due to its copper content and its relation to beginnings of metalworking in the island of Cyprus that has indeed lent its name for the metal copper, es cuprium. So here we can look at not just the human remains and other artifacts, but also explore the potential resolution to what those pendants could have been made of. And talking about faience, in Pakistan, beads and their particular structure made of faience, in this case, were explored to look at different manufacturing techniques and technologies. And in this case, tomography and a synchrotron was able to resolve these key questions about technology, about diversity of techniques. Here we see another case study looking at metal imitating pottery, in this case from Italy, looking at metal layers, the interfacial regions, and so on. Glass beads is another example, and here a multimodal, correlated multimodal data capture, correlated multimodal imaging, very much in the fore in terms of the European and global project scene in the sense of, for example, Comilis, cost action. Here the correlation is between the tomography and then chemical imaging using other techniques. Textiles is another group of remains where we can look at microstructures in this case. This technique was used to look at copper affected textile, wood identification of wood species, and this can be done non-destructively in terms of standard techniques. One would need to cut precious items, and of course we do not want to do that with the rare finds of wood. This slide was also shown by one of my colleagues earlier today, again bringing home the importance of multimodal data capture. Here you can see in the bottom of the image the different kinds of techniques. And of course, tomography should take place in the context of other types of data acquisition. Yet another example, this time from human bioarchaeology, the domain where I am active. And here we looked at a particular type of bony growth in the human ear canal, which arises from repetitive aquatic activity, people gathering resources from water bodies, whether they are freshwater or marine contexts. And why is this important? This over 10,000 years old example here comes from a context where we're looking at the so-called broad spectrum revolution, the precedent for agriculture, and of course domestication is linked to human populations settling down and creating the civilizations as we know it. Here another example in that context in terms of domestication of beans, and further examples looking at animal remains, looking at again which species, differentiating between them, and that is of course important when we look at trade networks, precious items such as ivory and so on, as opposed to perhaps local materials. So some of these applications hopefully spark you thinking outside the box in terms of what you could apply these possibilities or techniques in your research domain too. And on that front, let us now look at a little bit how you can become a future user. The resources listed here, I will show them one by one in the next set of slides. There is, of course, the BEATS webpage and a number of project-related aspects. Particularly, I would like to highlight, however, that beyond the online set of materials that is now accessible to you, even during the pandemic, there is, of course, always the option of contacting people directly. I know that Dr. Gianluca Iori, who is the BEATS Beamline scientist, would be very happy to hear from you to explore already at this stage the potential applications. And all others in our team at BEATS, we will be more than pleased to hear from you. Project coordinator, of course, Axel Caprolat included, and we heard a very nice talk from him earlier today. SESAME webpage is a very good resource with a number of important updates, both on the facility, and you can also go and have a look at light sources around the world from the lightsources.org. What I would urge you to do is, if you are interested in information concerning SESAME and BEATS, is do access the SESAME user portal. You can see the web address there, and do register. And that means that you will get all the latest updates directly from SESAME. Another resource is the SESAME Users Committee. And in this committee, there's a number of members from the different SESAME members, including some student members as well. And we have all agreed within this committee that people are also welcome to contact us according to our domains of expertise. So cross members and also outside members. So do please get in touch if you would like to discuss your ideas. The first point of call, of course, is the Beamline scientist, Gianluca Iori, to gauge feasibility of specific research and so on. Now, the user community building events, we are in one of those now. These are events that we organize in each SESAME member within the BEATS project. And at this time of the pandemic, we have unfortunately had to resort to the online presence, but we very much look forward to being able to visit you in person, as Dr. Lausi mentioned earlier today, and be able to interact with you in the future. Here, an example of one of our Pakistan events. And another important meeting to look forward to is the SESAME user meeting, where you can interact with existing and future users, as well as the Beamline scientists and the SESAME scientific director, technical director, other key individuals. Here's a list of the Beamline scientists, and do please contact both them as well as existing users. And here's a list of formats how you can do that. There are many ways to begin discussing the feasibility of your studies. Key is Gianluca, of course, as I mentioned. Other key resources, have a look at the LAMP project, which is a good support medium, as well as look at national platforms, micro-CT facilities, and beyond, in this case, an example from Cyprus. The key is to look at acquiring laboratory-based or data through laboratory-based instrumentation prior to accessing the relevant synchrotron beamline, identifying the questions and samples which really require SXCT and cannot be done in the laboratory. And such platforms do exist. They're often open to external users, as in the case of Biomera here. Now, I will not go into detail on how to write a good beam time proposal, because Andrea will be talking about it tomorrow. The key thing here is they have to be scientifically compelling, competitive, self-contained, and a must is to consult the Beamline scientist in advance to gauge feasibility, to gauge any specific needs, to gauge the number of shifts. And here the references to the various resources. And with this, I would very much like to thank you for your attention.
Thank you very much, Kirsi, for this interesting talk. So if there's any questions from the audience?
I have a question, Kirsi, about the heritage analysis samples. You know that hard X-ray can do damage to the materials. So when you do such heritage analysis samples, is there any kind of protection for this samples from hard X-ray to have some damage, or it is really is not a big issue? What I'm thinking about.
Thank you very much indeed, Mohammed, for this very important question. Dr. Greiber has, of course, drawn attention to one of the key issues when we are looking at cultural heritage and archaeological remains, which is when and how to make those decisions about what type of analysis in the range of non-destructive to fully destructive we undertake. Of course, in the grand scheme of things, when we look at analyzing archaeological remains in the standard conventional mode, we often had to resort to destructive analysis to get information on chemical or structural nature of the samples. So already it is a big step forward to be able to look at non-invasive and non-destructive or minimally destructive analysis. Of course, as we all know, synchrotron radiation-enabled techniques and approaches do cause alteration in the samples. And one type of alteration could be, for example, the discoloration of the human dental enamel when we look at some of these teeth using tomography in the synchrotron context. We know that this discoloration is reversible, either with UV light or leaving the sample on sunlight for a period of time. However, there are other types of alterations, and we must be very careful when we look at the results of the analysis to see what relates to the original state and what relates to the potential alterations. And there are whole workshops and a whole set of publications and discussions on these. In archaeology and cultural heritage, what we always do is we try to optimize the information yield, the data acquisition relating to key questions, and the potential damage to the samples. And this is indeed something that has to be carefully negotiated both with the curators of the said remains, whether it's museum professionals or otherwise, as well as looking at what is the scientific yield. So I hope that goes some way in answering your question. These are obviously complex matters, and I'm very happy to discuss these further if anyone is interested at any point.
Thank you.
Thank you very much. Are there any further questions at this point? If not, let us then move on to the...
Can I ask a question?
Yes, please.
Yeah, I'd like to thank everyone who spoke today and to the organizers of this event. It's the lectures so far have been really enlightening, and sure it will be a very productive meeting. I wanted to ask two questions. The first you might already have mentioned, but are we going to be able to get those presentations? I didn't hear if you said something about that.
Tell me again, if I understood correctly, you were asking if you can receive the recordings of the presentations.
No, just the presentations themselves, like PDF.
The slides, yes, this could be arranged. I see the project coordinator nodding. Dr. Axel Caprolat seems to be in agreement, and so do the other presenters. So we'd be delighted to send these to you.
Perfect, because there is a lot of very important information that would be useful to everyone. My other question is about also the samples, because, you know, in material science, people like to experiment samples in many different techniques and get more information about the samples by exposing it to more than one technique. So my question is, what sort of sample size is needed for this kind of experimentation?
So if I may, thank you very much, Professor Al-Gharadawi, for this question. If I may briefly mention just from the point of view of cultural heritage and archaeology, and then I will pass to Dr. Gianluca Iori, who can discuss the sample sizes in more wide-ranging view for beads in particular, and of course other techniques. And this gets us also very nicely to the panel discussion. So at this point, if I may interject just before answering that question, to introduce to you Professor Ilham Karadawi and Dr. Mohammad Garaibe, who are our panelists today, in addition to all of us from the BEAT project. Professor Ilham Al-Karadawi is Professor of Physics at Qatar University and Adjunct Professor of Physics at Texas A&M University in Qatar. She received her PhD working in the field of positron physics from University of London. And over the past decade, she has established a positron laboratory at Qatar University and successfully built the first slow positron beam in the Middle East. She has also established an environmental radiation measurement laboratory and is involved with Europe's CERN in the anti-hydrogen experiment Aegis. She is the founder of the Qatar Physics Society. I'm just wondering if there is someone who is not unmuted. There is some background noise. If it's possible to mute for a moment. Dr. Ilham Al-Karadawi is a fellow of the Institute of Physics and a member of many international societies. She also sits on the advisory committee of the World Nuclear University Radiation Technology Summer School and the World Council on Isotopes, and has lectured in the World Nuclear University Summer Institute for the past 4 years. Professor Ilham Al-Karadawi has been awarded many awards for excellence in research, for Arab women in science, and outstanding contribution to science. And she has had many appearances on Al Jazeera channel and several other TV channels and newspapers and magazines. She has also been listed by the Arabian Business Magazine as one of the 50 most influential people in the state of Qatar and one of the 500 most influential Arabs in the world for the year 2012 and 13, and one of the top 28 Arab scientists in the world, and by CEO Middle East Magazine as one of the 100 most powerful Arab women for the year 2012. So it's really a pleasure to have you with us, Professor Al-Karadawi, and we are very happy to interact with you in this panel discussion occasion. It's now also my pleasure to introduce Dr. Mohammad Garaibe, who is also here with us for the panel discussion. Dr. Mohammad Garaibe was the main proposer to a research group on studying K-shell photoionization of nitrogen isonuclear sequence and K-shell photoionization of oxygen isonuclear sequence with his colleagues in France, and mainly Dr. Jean-Marc Bizot from the CNRS and Paris Sud University, France. They had an experiment at Maya end station on Pléiades beamline at synchrotron Soleil in France, and they explored the inner shell photoionization of nitrogen N and O ions. He has been studying the electron impact ionization of multiply charged ions during research visits to the Institute for Atomic and Molecular Physics in Gießen University with his colleague, Professor Dr. Alfred Müller and his group. And they studied ions over 4 summer visits. He has been studying during his PhD the photoionization of ions in Professor Panov's group at University of Nevada in the USA, using the ion photon beam end station located on Beamline there at the Advanced Light Source in the Lawrence Berkeley National Laboratory. And his dissertation title was Systematic Photoionization Study along the Iron Isonuclear Sequence. Okay, so very warm welcome to the panel discussion, and if I may then return to the question of Professor Al-Qaradawi briefly in terms of cultural heritage. Sample sizes, they are very much determined by the technique and the approach. Our general principle with cultural heritage and archaeological objects is that we do not want to alter them. So therefore, tomography lends itself wonderfully for this, and especially beamlines at synchrotrons that are able to accept even the larger samples, though we're interested in a very small area, given the type of technique and its high resolution. We do not wish to, of course, cut these unique artifacts. But perhaps I could ask Gianluca to discuss further the sample sizes. Gianluca, would you like to take over from here?
Yes, if I may, I could share quickly one of my previous slides on sample size. Can you hear me well?
Yes, we can.
There is some echo, maybe the room itself could be silent, I think. But anyhow, this is a brief, like an overview of the beam size at the position of the experiment, which of course determines how big a sample we can illuminate. And as you see, the beam will have, this is a simulation, but the beam will have a width of 40 millimeters by up to 15 millimeters, which determines more or less the maximum size that you can illuminate with this. But on top of that, you need to have a detector that can see that. So different detector field of views are overlaid here from a maximum field of view of 16 times 1606 times 14 millimeters with a pixel size of 6 micron, going down to high resolutions, but you image only a few millimeters. So maximum size of the field of view of 1 or 2 millimeters. Of course, this has also this must also be taken, let's say, relative to the material you put in the beam. If it is a dense material, you cannot see through 10 or 20 millimeters of a dense material, and you would need to go to smaller sample size.
Thank you, Gianluca. Professor Al-Qaradawi, would you like to comment further? Does this answer some of your, or indeed all of your question, or would you like to make some further comments? And please also feel free to comment on the day's menu of talks and the potential for Qatari users for applications of the Beamline. Professor Al-Qaradawi.
Thank you, and Chrissy, for these answers. So it seems to me like it depends on the application, what sample size and also thickness we can use, but general, it's within the limits of the material science samples. So it's really good. I'm sure that many of the attendants here from Qatar would be interested in many of these applications because they cover mostly almost everything in material science. And I think it's a very good opportunity for people to have this option of measuring their samples with such advanced beams and a different type of technique, which certainly gives a lot more information and helps material science in many ways. So thank you everyone for briefing us about this technique and about beads, and we hope to be able to join in projects and apply for grants and so on in the very near future. Thank you.
Thank you very much indeed, Professor Al-Qaradawi, for your comments, and it is indeed very important for us to be able to interact with you during this event, and we would be very pleased to hear from you and indeed all of your colleagues in Qatar regarding the future potential for applications at the Beamline. May I invite some comments now from Dr. Garaibe regarding the beats and potential for Qatar, as well as any comments on the day's menu of talks, let's say.
Thank you, Kersi. Many thanks to everyone who briefed us about beats in more details. And really, it's very helpful, and especially how to guide us to go to be as a users of beats or SESAME in the future. There is some Qataris, they are users of SESAME before I became as a user, so which is something very interesting that to have SESAME in the Middle East, which is make it easier for us to do some sample research in the Middle East with less competition comparing to the others with synchrotron facilities in Europe or USA, which who is in this field, he knows that the competition is high when you gain a beam time. It is something luxury, so it was not easy to have experiment in Soleil, and still struggling to get beam times in Hamburg, in Daisy. So, but when we have SESAME in the Middle East available, which is already available, that's really very interesting. And this is why I'm trying to make SESAME is one of the research center that researchers here in this country can look for to do research there. And it will be nice that I know that there is many summer schools and other workshops but now with the COVID-19, that make it kind of impossible. But I don't know if Qatar, since is not a member state or observers of SESAME, is it possible that these kind of workshops specified for member states of SESAME can be also available for others to attend, participate, not looking for fundings for attendees for such summer schools or workshops, specified ones can be organized by SESAME or other committees. Is there any answer for this? Please, is there any chance for us in Qatar to participate and get more about what we can do in SESAME in the future?
Thank you very much indeed, Dr. Garaibe. May I ask Dr. Lauzi, the scientific director of SESAME, to comment on this? Dr. Lauzi.
Yes, of course. It's I think that the fundamental things here is to make the SESAME more available to the building of the community. Unless this is the importance, and it's also the meaning, the essential meaning of SESAME. So I'm really looking forward to the moment in which people will start traveling again, because the interaction at the venue, at the premises of the synchrotron is of extreme importance in order to share knowledge, in order to get more information and to perform better experiments. It's very difficult to engage a community just with sending samples and working as an analytical facility. This can be done in certain niche of science. For example, it is done since many years in macromolecular studies. So we want to know where the atoms of the macromolecule are, but that is because that is essentially a measurement and not an experiment of the entire process, getting from the protein to the structure of the protein. The measurement at the synchrotron is an essential and necessary step, but is by far the shortest and the easiest. And it has been made automatic. So in many cases, also within leaps, we are speaking of beamlines, which a beamline can align itself and do all experiment itself, but always only for some particular kind of measurements. For the general user, being here is much more important than sending the sample successfully and just get a few numbers out, a spectrum out of it.
Thank you very much indeed. Further comments, topics for discussion, queries from the audience, or indeed the panel discussion participants. I see Dr. Hanoun, please.
Thank you all for this for building this great facility. I want to ask you when the facility will be available for users, especially users from Qatar, and will it be different for the beam time allocation, for example, for people from Qatar or for national from Jordan?
So again, I would ask Dr. Andrea Lausi to respond to this question. Andrea.
So essentially, okay, the facility is open since 2018, receiving and performing experiments since 2018. And essentially it is also open to, on the basis of scientific merit. So what happens with the proposals, they are judged by a international project review committee, which puts them in order of scientific merit, and then the beam time is allocated on the basis of that list.
And for the tomography beamline, will it be at Q1 of 2023?
2023, yes.
Yes, thank you very much.
Thank you for your question. Other questions, comments, or queries at this point? We, of course, have the opportunity to continue our discussion tomorrow in the framework of further talks, as well as the breakout sessions. So tomorrow we have 2 further talks, and I'm very happy to see here also Professor Riyad Al-Raoush from Qatar University, who will be speaking to us tomorrow about synchrotron microcomputed tomography for geoenvironmental applications. Thank you very much indeed in advance, Professor Al-Raoush. And we also have a talk on data analysis and management for the Beamline for tomography at SESAME from one of our BEATS team members, Dr. Haralambos Chrysostomou. And of course, very importantly, from Dr. Andrea Lausi, as mentioned, the scientific director of SESAME, a tutorial on how to apply for beam time. So this is a very important practical opportunity to engage with Andrea and get crucial information and tips on how to obtain and secure that important beam time for your research. And then we have the breakout sessions, followed by discussion and closing remarks. What I would like to suggest before we go today, we have not indicated in the program, but if everyone is happy to have a so-called group photo taken, we often have these kind of photographs in the in-person meetings. I see Dr. Garaibe in agreement. If every one of you who is, and also Professor Garadawi, so if those of you who would wish to participate in a group photograph today, we will also have another opportunity tomorrow during the middle of the session. But please feel free to turn on your video now, if you're able to. We will just give you a few moments since we did not announce this in advance, but our team members will here take a screenshot so that, and also the interns who have been following, please feel free to turn on your cameras if you would like. Is everyone now ready who wishes to turn on their cameras? We will take a few moments still. I see people are still putting their cameras on. So let's take a few further moments to make sure that we have everyone who wishes to turn on their videos. Now I think we are as complete as we are going to get with this more informal photograph. We will have a more, let us say, formal photo tomorrow, right after Dr. Andrea Lausi's tutorial on how to apply for beam time proposal, or I suggest. So, okay, here we are. Ready? And I believe we are done. Very good. So thank you very much indeed for everyone for participating in today's meeting. We're delighted that you could join us today here at the Cyprus Institute Green Room, and we very much look forward to interacting with you tomorrow, same venue and same start time. And even more so, we look forward to an opportunity to meet you in person in the future. Stay well, stay healthy, and see you tomorrow. Goodbye.